Oops, I pushed the wrong button apparently. So we're going to look at reactions of aldehydes and ketones, but what we should realize is that we're also going to be having alcohols mixed in there. And then the other thing that we have to kind of pay attention to is that we know on the next test that we're going to have aldehydes, ketones, alcohols, and ethers all mixed together. So hopefully everyone's got a good understanding of the previous set of reactions and has, we did that review session, and hopefully you've kind of figured out a way to recognize all those types of reactions. So now that you can, so that you have that, you can now kind of build on these new reactions. That being said, a bunch of the reactions in this section are actually just repeats of reactions in the alcohol chapter, because one of the reactions that we talked about was, we know that if I take a let's start on a new slide. If I take a primary alcohol, what does that get oxidized to? An aldehyde plus H2O, and that gets oxidized to carboxylic acid. And if I do the secondary alcohol, that goes to the ketone plus water. Good morning, Jasmine. And then there's no reaction for that, right? And then, of course, we'll just, for completeness sake, we'll throw the tertiary alcohol as no reaction. And so we learned that whole scheme when we're talking about alcohols, because it allows us to differentiate mostly between the secondary or primary and secondary versus, say, a tertiary alcohol, meaning we can tell if it doesn't react. But now, if we were looking at aldehydes and ketones, these make very good tests to differentiate between an aldehyde and a ketone. Aldehyde will react and give a positive test if there's some visual evidence associated with it, and a ketone won't react and give us a no reaction. So we have some really good tests to differentiate between aldehydes and ketones, especially with sort of visual clues being included in there. Now, you guys did all of those tests, or at least a subset of them, on Tuesday, and you'll finish up on Thursday. And so when we're going through these, try to link what we're doing on the board here with what you actually did in lab, at least as far as the visual evidence and whether your aldehydes and ketones behave nicely, or if your aldehydes and ketones maybe didn't behave so nicely. So the first one we're going to talk about, and I should point out that this is oxidation, right? And remember that this stands for generic, meaning we don't keep track of all the reactants and products. We don't even show what's being reduced in order to oxidize the other compounds, or to oxidize the organic compound. And so what we're going to do with the specific reactions is we're going to look at specifically what compounds are oxidized and which one is reduced to kind of pair up with it. And maybe we should do just a tiny bit of review before we get started. What is oxidation and what is reduction? You guys remember that? It'll be on the test or the next test, or guaranteed it's in the biochemistry chapters. Which reminds me, Taylor, when we flipped forward in the book, how many times were we able to flip forward and say, oh, that's something that we've already studied? 4 or 5 out of 5 times? Yeah. So as a reminder too, everything that we're doing now comes back, or at least I should say probably like 75% of what we do now comes back in the biochemistry chapters. So you master it now, you get to the biochemistry chapters and you don't even have to study for half the material because you already know it, hopefully. So what's the difference between oxidation and reduction? Yeah, lose electrons, and yeah, so that's the Leo part, and that's the Gur part. So what we're really doing when we say we're doing an oxidation reduction, if we're really keeping track of it, meaning we're really looking hard at the reaction and we're writing all the reactants and products, we should see that one molecule or atom loses electrons while another molecule or atom is gaining those electrons. What are some other signs that we said that usually is associated with it but doesn't always have to be there? Meaning electron gain and loss is the definition of oxidation reduction. That's where the true definition lies. The other things that we say are all signs that that's likely what occurred. It was gaining and losing bonds to oxygens and hydrogens. Do you guys remember which is which? Study for the test. So we usually gain bonds to oxygen, we lose bonds to hydrogen, and here we gain bonds to hydrogen, lose bonds to oxygen. Now I have to be honest, that's a 50-50 thing with gaining and losing, and 50-50 is tough to keep track of, right? Meaning it's easy to get flip-flopped in your head. And I showed this as a trick before, but we'll redo it now. Let's talk about how we calculate oxidation numbers and give you an example that if you memorize that example, you should be able to remember whether you're gaining and losing hydrogens and oxygens for each of those definitions. So remember, what an oxidation number is, so what we're talking about when we really talk about oxidation reduction reactions is that oxidation number is changing, is that's the theoretical charge on an atom, assuming we gain lose electrons instead of sharing. And so what it's saying is, instead of treating things like they're molecular compounds, instead treat them like they're ionic. So we kind of treat everything like it's ionic. And there's some simple rules, and the rules I'm going to give you are not the complete set of rules, because of course, where would chemistry be if there weren't exceptions? But we'll never encounter the exceptions in this class, and so we won't worry about it too much. Or if we do, we'll point out where that exception is. So for instance, hydrogen is always a +1. And that makes sense. What are we used to seeing when we balance ionic reactions? Hydrogen is always +1, right? Oxygen is always, what's the charge on oxygen? -2. Now, in some oxidation reduction reactions, we'll see that that charge can change, but that in general, that's the charge on that ion. If I have a element in its natural state, its oxidation number is 0. So examples are, for instance, if I have sodium metal, that's a solid, it has an oxidation number of 0. Now we usually show oxidation numbers where we show charges, so sometimes we'll put a 0 there. And some books will instead write it underneath the atom and put a 0 there. So, you know, I don't know which way I'll end up doing it. Usually I write it underneath because there's already enough stuff up on that upper part. Or, for instance, if I have oxygen gas, in this case, oxygen has a oxidation state of 0 because it's in its natural state, meaning it's just oxygen gas. And they're sharing those electrons perfectly, so it doesn't really, one doesn't gain some electrons and one doesn't really lose some electrons. If it's a neutral molecule, actually I'll do this on the next slide. Oops. So for a neutral atom or molecule, the sum of the oxidation numbers equals 0. And what that does is that allows us to determine the oxidation numbers of other elements. For instance, if I have HCl, and I know the oxidation number on hydrogen is always +1, what does chlorine have to be if the total is 0? Yeah, this has to be -1 because when I add those up, they have to be 0. And where this comes into play is when we have variable charge metals that we need to do things in. For instance, if I have KMnO4, that's one of the ones we're used to, right? What's the oxidation number of all the elements there? Well, what's oxygen always? And we know that potassium normally is a, since it's on the first column of the periodic table, not -1, but a +1, right? Meaning it's in the same column as sodium and lithium and things like that. And so then what we have to ask ourselves is, what's the oxidation number of manganese? And so if we take a look at it, what we're really saying is I've got the following math statement, that 1 times 1, since I have one atom, plus 1 times x, since I don't know what manganese is, plus a -2 times 4, since there's 4 of those, all has to be 0. Or think about it this way. the whole molecule has to have all the charges add up to 0. So you're used to balancing the charges on molecules. So if you don't like that math equation, go ahead and kind of do it in your head. How many negative charges do I have total? Times, no, I've got 4 oxygens, right? -2 each, so 4 times -2 is, right? How many positive charges do I have? 1. So how many more positive charges do I need to have that be 0? 7. So here, X, or the charge on manganese, is +7. And then since we're talking about oxidation reduction reactions, on the opposite side of that equation I have manganese oxide like this. What's the charge on each one? Yeah, oxygen's always -2, and so manganese must be +4, right? So notice that on one side of the equation it's +7. On the other side of the equation it's +4. So to go from +4 to to go from +7 to +4, how many electrons does it have to gain? 3, right? So if it gained electrons, that means it was oxidized or reduced? Reduced, right? And remember when we wrote that reaction, in fact, maybe we'll just write it up real quick. So we've seen this in a variety of formats. The one we saw in lab was like this, right? Meaning I take a, wait, did we do the alcohols or was this in the aldehyde lab? This is the alcohols lab, right? Plus KMnO4. And we said that that gets oxidized to an aldehyde, right? Plus MnO2 plus KOH, and in this case plus H2O to make it balance. So that was in your lab. And so notice that here, if this has a +7, and here this has a +4, means that this was reduced, right? So what was oxidized in this reaction? Well, the manganese was reduced, right? It gained electrons, so it gained 3 electrons. What was oxidized in the reaction? Because remember, we called this an oxidation reaction when we covered it in the chapter on alkenes and alkynes, and we called it an oxidation reaction in lab. So what got oxidized? Well, +7 means it's missing 3, right? Or missing 7, I mean. +4 means it's missing 4, so it must have found 3 at some point. So it gained 3 electrons. So what was oxidized in this reaction? There's a reason we call all those reactions oxidations, right? What gained bonds to oxygen here? Yeah, we said that alcohols get oxidized to aldehydes. And so that's oxidized. The way we kind of see it is that the easiest way is that we gained a bond to oxygen and we lost a bond to hydrogen, technically, because remember, in this molecule there's 2 hydrogens here, and in this molecule there's only 1. So I both gained a bond to oxygen and lost a bond to hydrogen. In fact, I actually lost 2 bonds to hydrogen, right? And so in one case it's easier to count the electrons if we're talking about just a simple metal like manganese. In the other case it's probably easier to focus in on the atoms that are there for, gaining bonds to oxygen and losing bonds to hydrogen. Let's look at another example of oxidation reduction. So we should be familiar with this reaction. What type of reaction is it? Oops, not 2. Yeah, so we know that we go to CO2 plus water. And notice I'm drawing the structures, mostly so that we can easily identify what the oxidation state of those atoms is, because in order to figure out the oxidation state, you kind of need to know a little bit about the structure.
How does carbon have 2 lone pairs?
Oh, sorry. Got carried away. Those lone pairs go on. Oxidation. I knew they had to be somewhere. Aaron, I'm impressed. For this early in the morning, brilliant. Brilliant. So, let's calculate the oxidation number of things. Now, hydrogen is always +1, right? So that's uninteresting, meaning I can go and I can label all of these as +1. It's kind of boring, and usually I don't even bother labeling it. But since this is the beginning, we'll put it there. What else do we always know? Yeah, here it's -2, right? But what is it here? 0, right? Because it's in the element state. So that leaves us with the carbon on both of these molecules. What's the carbon in methane have for an oxidation state? If all the hydrogens are +1, to make 0, what does carbon have to be? Not -1. There's 4 hydrogens, right? So it has to be -4, right? And what about the carbon in the oxygen? Yeah, it has to be +4, right? So what things changed oxidation numbers? So carbon went from -4 to +4, right? Oxygen went from 0 to -2, right? Those are the things that gained and lost electrons. Hydrogen stayed the same in this case, right? So who was oxidized and who was reduced? Oxygen, well, let's see, the carbon had 4 extra electrons, right? It lost all those, so we would say that this is our reduction. And Brittany, I heard you say that the oxygen was oxidized because you thought it sounded funny, which it does. And it's true. It gained electrons, right? Wait. Okay. Stop for a second. Because this is too easy. This is 50-50. So let me double check my thoughts. We have that backwards. I have a tough time thinking about it this way. I think about it another way. Carbon was carbon oh no, carbon was oxidized. And this was reduced. See, this is 4 extra electrons. This is missing 4 electrons, right? Meaning it had extra electrons, now it's missing some, so it lost electrons, right? And it's weird because by losing electrons, it got more positive, right? Meaning one way you can keep track of oxidation reduction is some people will say if the number gets more positive, then it's an oxidation. If it gets more negative, then it's a reduction. That's a 50-50 thing. I get lost too. I just have to picture where the electrons are going. And then the oxygens each had to gain electrons to go from 0 to -2. And so what that really means, meaning what we get to the biochemistry chapters, and when we're looking at oxidation reduction reactions, come on, just give me a different color. Oh, boy, it's really slow today. I really, really, really want a red pen. So, what we really want you to be able to recognize is that carbon was oxidized. And oxygen was reduced. Meaning in every oxidation reduction reaction, somebody is oxidized and someone is reduced. We've been labeling reactions as simply oxidation so far because what we've cared about is the organic molecule, right? We haven't cared about what's being reduced. But what you're going to see is that when we pair it up with these other compounds, we're going to have something that we can track that's oxidized and something that we can track that is reduced. And it's that pairing of those reactions that allow us to differentiate between aldehydes and ketones. We kind of got off track and we kind of reviewed a lot, and we added a bit of new stuff. The other way that I also like to think about this is we know that if things are reduced, we store energy. And here, this is we've lost the energy. Because what do we really have when we do this reaction? Plus energy, right? Or heat, or we release that energy from those carbon-hydrogen bonds. And so carbon-hydrogen bonds tend to store energy. Carbon-oxygen bonds tend to, well, don't store any energy, and they're usually the end result of a process. For instance, what do we exhale all the time? Carbon dioxide. What did you say? I don't even want to know. We inhale oxygen, right? She might have misheard me. We'll just say that. So we inhale oxygen, right? We reduce that, and we exhale carbon dioxide. That's the other half of the process of us eating food and taking that energy and oxidizing it so that we can have energy to move around and do stuff. And that's what the last 4 chapters in the book are all about, bioenergetics, following the energy flow in our body. So we got way off topic, but that's okay because we wanted to break this apart into 2 days anyway, I guess. So we're going to look at the toluene's reaction, which you did in class. And remember that this is just an oxidation. And the key here is that you want to remember what happens to it. So we have an aldehyde plus 2 silver ions plus ammonia. And we oxidize that. And now normally what do we oxidize an aldehyde to generically? Right. Well, here it's almost the same. We're going to have our carboxylic acid, but we're going to make what's called a salt. Plus, of course, 2 silver ions that are just that. And the idea is that this is a clear solution, right? And that this is a silver, oops, not sliver, silver mirror. Meaning that we got a coating of silver on our glass. And it's actually this reaction that they used to use to actually make real mirrors. Now they have better reactions to do it that make it nicer looking and things like that, more durable, things like that. But this used to be the old-fashioned way to simply make mirrors.
What do they do to it when it is clear? Like instead of like an actual reflection, it's like warped.
Good question. My initial answer is I don't really know, but if I'm going to take a stab in the dark, I'm going to simply say that it has to do with the flexing of how the mirror is bent. That's what causes the distortion in your thing. Whether they do that by physically deforming the mirror or having different thicknesses of silver, I'd like to think that the easy way would be to simply deform the mirror, and it doesn't take probably too much to deform it. So that's my easy answer. If you remind me, maybe I'll Google it and find a real answer.
Or I can Google it first.
Sure. Which reminds me, Alyssa, I did get your text. You'll just have to remind me sometime again when my computer's in front of me. So, let's take a look at what happens. There's an aldehyde, right? Plus my 2 silver ions plus my NH3. And I guess if I'm being really good, I should put in that those are aqueous and so on, but we're not going to worry about it. Now, what does a carboxylic acid normally look like? And then it has a bond to oxygen, right? Now, when it forms this salt, instead of having a hydrogen attached to it, it's an oxygen minus charge, because remember, ionic salts are pluses and minuses, right? And then the other half of the salt is NH4 plus. And so, because NH4 is ammonia, we sometimes call this also ammonium salt. plus 2 Ags. And so remember, if we think about our aldehyde there, that's already got a hydrogen, right? And so the way I kind of think about this reaction, although I have to be honest, this is almost brute force memorization to remember that it makes the carboxylic acid salt. I mean, it's not a big leap because we already know what makes the carboxylic acid, is that, you know, there's our NH4 kind of, right? And then remember, we always get an O from our oxidation, right? Or we can always get that. Now again, I'm not even showing the complete reaction. How many people enjoyed balancing that reaction yesterday in class that was oxidation reduction? How many people actually did balance it? Yeah, it was ugly, wasn't it? And this is why we're not going to worry too much about balancing these reactions, because they're fucking ugly, to be honest. And I don't like fucking ugly, so we try to not balance them. So we can kind of see what happens. And then we can tell it's an oxidation reduction because what's the oxidation state of silver? If it's just the ion, it's +1, right? And over here, it's -1. So what happened to that silver? Was it oxidized or reduced? Yeah, it had to gain an electron. In fact, it gained 2 electrons, right? And therefore, that's our reduction. And if we take a look at our aldehyde, this must be our oxidation because we gained a bond to oxygen, right? Oops. Now, we could go and calculate the oxidation state of the atoms in that molecule. And in fact, maybe well, I don't know, should we do it just for fun or not? What? I was going to say, it's not going to be on this test, but it will be on a test in bioenergetics, just so you know. So it's not something, so it's something that you have to learn. So anyway, there's the toluene's reaction. Easiest way to recognize that is the Ag+. At some point in your brain, you just have to associate silver and toluenes, right? What was the other one we did in class? We did do Lucas, but we've already covered that. This is called Fehlings and Benedicts, and sometimes it even has more names. And so the exact chemicals used vary. But the general formula is the same, meaning you're going to have different books give you different recipes to make up the Fehlings A solution and the Fehlings B solution we used. And usually the only difference between them is whether the copper comes from, say, copper sulfate or if it comes from some other compound. And so in this one, we're going to have an aldehyde again. Now, why am I not writing the reaction for ketones? Yeah, so if you see a ketone in here, you just write no reaction and I'm happy, right? So don't forget that there is the no reaction side of this. Plus some copper ions. Plus some sodium hydroxide. Now if I oxidize this, I make again a carboxylic acid salt. Plus, in this case, Cu2O solid plus H2O liquid. And if you guys remember, this is a pretty blue solution. And this is a brick red precipitate or solid. So that's our visual evidence that a reaction is occurring. Because for instance, if we did just a regular oxidation reaction with an aldehyde without something that changes color associated with it, quite likely we'd turn a clear solution into a clear solution. So we've got to pair it up with something. In this case, we're pairing it up with those copper ions. So here's my aldehyde. And again, the rest is just tedious copying down of stuff. And what does an aldehyde always get transformed into? carboxylic acid. And then see, here's the new part. Remember, it's the salt, right? So we have an O minus. What's the cation going to be there? In the previous reaction, we had the ammonium cation, NH4 plus. What cation do you think we're going to have here? What? Not NaOH, because that's the entire compound. Just the... Because sodium is a cation, right? And then the copper was not a horrible answer, but we should know from looking at the reaction that that gets stuck with the oxygen and then the plus H2O. So the tricky parts in these new reactions is memorizing all of the extra parts. Now you don't have to memorize the parts on the left, you just have to recognize when you're reacting things with silver, it means toluenes, and when you're reacting it with copper, it means phthalings or benedicts, right? Right here. And that if you're reacting it with silver, you make a silver mirror, and if you're reacting with copper, you make copper 2 oxide, right? And a carboxylic acid salt in each case. Well, you guys did the reaction. Who did both reactions in lab yesterday? Which one would you rather do if you had to really quickly determine whether it's an aldehyde or a... Which one? Why? I personally thought the toluenes test is quicker just because, you know, it's red to blue or blue to red, and you just have to have boiling water for 5 minutes. The other one seemed like it took a lot longer for people. But I would say they're both equally good. So you only got one positive? You better take a look at that on Thursday then. See what's up. Huh. Contaminated test tubes. Contaminate your test tube. Okay, anyway, getting off track here. And then remember, for both of these, if it's a ketone plus the silver ions plus the ammonia, you just get to write no reaction. And if it's a ketone plus the 2Cu plus 2 ions plus the NaOH, again, you get to write no reaction. I got to be honest, every time I see a ketone in a reaction, since I know about half the time it doesn't react, I simply just cheer. I'm like, ketones rock. I'll be back in 1 moment. Sorry, being sick is fun. Okay, next set of reactions, we're going to change pace a little bit. Now we're going to get our first taste of a reduction reaction. Now remember, they're all paired anyway, right? Meaning that anytime a reaction is labeled oxidation, something is being reduced. And anytime we reduce something, something else is being oxidized. What determines whether we call it an oxidation or reduction is what happens to the organic compound. So for reduction reactions, the arrow we're going to see is something that looks like this, where we have to have heat, we have hydrogen gas, and the nickel acts as a catalyst. Does anyone remember what a catalyst is? Speeds up reactions, but doesn't change during the reaction, right? And so, you know, it's on the reaction arrow, but we never write it in the reaction, but it is required for it to occur. And what reduction reactions do in this type is we can also label them as simply additions of hydrogen across a carbon-oxygen double bond. So is this a new reaction? Actually, there's no question mark there. Not really, meaning you've had this reaction. You know how to do addition reactions with carbon-carbon double bonds, right? Did addition reaction with a carbon-oxygen double bond change? No, it's the exact same thing. So in this case, if I have an aldehyde and I reduce it, I turn it into a primary alcohol. Meaning if I take my favorite aldehyde, the one with 2 carbons, because it's the easiest one to draw, right? And I think about that as I'm adding hydrogen gas. So that means a hydrogen goes on one side of the bond, and a hydrogen goes on the other side of that bond. And I'm simply left with OH. And then we don't normally draw that H there, but I'm going to show it there to show how we broke that double bond. So this is exactly like the addition reactions in, I don't remember, chapter 19 and 20, where we took a carbon-carbon double bond and we broke it and added hydrogen across the double bond. So it hasn't changed. The only thing that's new here is the reaction arrow, right? Because we showed addition reactions and those other ones differently, right? So new reaction arrow, same old process. So I consider this a 50-50 one. You kind of learned something a little new, but if you remembered the old part, then it's not too bad. What do you think happens if I have a ketone? Oh, hold up. Yeah, it goes to a secondary. Ketone, hydrogen, nickel, some heat, goes to a secondary alcohol. And so again, I'm thinking about it as adding hydrogen to one end of the double bond, adding hydrogen to the other end where that carbon is, and I get an OH group, and I'm really adding a hydrogen on that. Now, do you have to show the hydrogen that's added on the carbon? Technically, no. Is it useful to show it so that you kind of see what's going on and it sticks in your brain and you know why it's there? Probably. At least that's my opinion. Will I mark it wrong if you don't show that hydrogen? No. Will the computer show that hydrogen? No, because the computer's freaking lazy, right? It doesn't like to show the hydrogens unless I make it show them. And I didn't make it show them because I'm lazy too. So, I personally think this is a nice, short, sweet, simple, easy reaction. If you can recognize it, and if you can link up H2Ni and heat means add hydrogen across the double bond, you're pretty much all the way there. And then the other thing that we should be recognizing is that because we have aldehydes and ketones, they have that carbon-oxygen double bond, right? And so almost every reaction is going to be involving that carbon-oxygen double bond, because what do we know about the pi electrons in that double bond? Super reactive, right? And so we expect that that's the part of the molecule that reacts. So we have a series of 1, 2, 3, kind of 4-ish, depending upon how you talk about it, 4 different types of addition reactions. The first one is called a cyanohydrin reaction. And what it really is the addition of HCN across a carbon-oxygen double bond. I feel like I should just draw this up here. In fact, what the heck, we'll just off to the side here. Before we even talk about what things happen. Can you tell me what's going to happen? Just by what we've talked about. I should point out that usually it has to be in basic conditions. Before I even say what happens and what's formed, what can you expect to happen? Something has to be added here, right? And something has to go on that end, right? And so what we find is that the hydrogen goes here, right? And the CN is going to go there. Meaning, I break just like I break hydrogen across and add something to each half, I'm breaking HCN not quite in half, right? When I'm adding something on each step. And so if we say this in words, what we get is that an aldehyde or a ketone plus HCN, oops, not oxidized, OH minus, reacts to make what we call a cyanohydrin. Now, I have to be honest, does the word cyanohydrin mean anything to you yet? No. And so when we draw the reaction, we'll show you what a cyanohydrin is, and you'll see why that's why we call it that. So take Jay's favorite aldehyde plus HCN. Oh, I keep forgetting to throw the H in there. And then remember, I'm breaking apart this at the H and the CN part. The H goes there, the carbon goes over here, and I get something that looks like this. I get an OH, and I get a bond to that new carbon. And I should point out that that carbon is triple bonded to a nitrogen, meaning if I take a look at the structure of HCN, the Lewis structure looks like this. And so when the computer draws it, it'll kind of draw it like that. Or maybe I should point out that that's how I draw it. And so the reason it's called a cyanohydrin is this is a cyano group, and this OH is kind of like a hydroxy, or when it's paired up with the cyano group, we call it a hydrin in this case. So that combination of the C triple bonded to a nitrogen and an OH makes it a cyanohydrin. So a new vocab word for you. Pretty good one to use in Scrabble if you got two Y's. Buku points, right? I'm going to do lots of examples here. So this is how I'm drawing it, okay, to show where all the parts come from. What the computer is going to draw is something like this. And I might even have this wrong, but it tends to draw it like this. Meaning it shows a triple bond to nitrogen, and it doesn't show that there's that carbon there, but there really is 3 carbons, right? 1, 2, and that carbon there is a dot too, kind of, right? So it doesn't show the carbon triple bonded to an oxygen explicitly, it simply shows it as a carbon triple bonded to a nitrogen. So the computer does it differently. And I should even point out, I'll bet you it won't show it like that. We really should show it like this. Why should I show it like that? It's linear, not bent, right, with that triple bond. So the computer's better than me. I tend to draw things however I want. The computer likes to get at least the bond angles right most of the time. Now it is a bit lazy. It won't show the hydrogens unless you make it. But so that's how you're going to see it on the practice and on the test and maybe on the homework. Okay, let's look at a ketone example. So again, I'm thinking I add the hydrogen on that side of the double bond. I add the carbon on that side of the double bond. I get an OH group. And I get a carbon that's triple bonded to a nitrogen. And I got to be honest, I draw that nitrogen pointing down. The computer could draw it any way it wants, right? Meaning, if the computer wants, it can draw it like this. Oops. Meaning that's the same answer. So one of the things you should do is when you draw something and when the computer draws something, compare them pretty carefully, right? You got to be a little flexible in checking your answers. Oh, I was confused for a moment. So one of the reasons this reaction is important is this is the first reaction to make a carbon-carbon bond. This is the first time that we've shown the making of an actual carbon-carbon bond. And so if I want to take a small molecule and build it up into a big molecule, this is one way to do it, right? I can add a carbon at a time. And we'll see this reaction again in the chapter where we talk about building up molecules or making bigger molecules. Now, arguably, this is the way a chemist does it. Your body doesn't tend to use hydrogen cyanide because it's toxic. But we use that as chemists in a beaker. Okay, let's do one more set of things to get you started. So there's a series of reactions that are going to make molecules, and we want to talk about their names. So just like a cyanohydrin is a special name for a type of molecules, we're going to have things that are called hemiacetals and hemiketols. Now, what's the difference between an acetal and a ketol, do you think? Ket sounds like ketone, right? So it's going to come from ketones. Acetal doesn't really sound like aldehydes, but it certainly doesn't sound like anything else either, so it's the one that comes from aldehydes. And a hemiacetal is a molecule that has a carbon that is bonded to an OH group, an OR group, a hydrogen, and an R group. And so, if we think about it, the reason it's an acetal is because it has that H, right? And so the hemiketol version has the same part. It's going to have an OH, an OR, but it's going to have two R groups, right? And so because there's two R's, it's equal to a ketol. And so notice that this occurs in the middle of a molecule. This occurs at the end of a molecule. Just like, gotta sneeze. So, you know, this is coming from an aldehyde in a reaction, and we're going to find that this comes from a ketone in a reaction. And then, what does a hemi mean normally to you? Half, right? Like hemisphere. I don't know what it means when you're talking about trucks. That makes no sense to me either. But I was just waiting for Jess to think of trucks. So what the hemi part means is that it's half alcohol, half, what does OR really stand for? Right, what do we call that functional group? Last chapter, you guys are killing me. COC is a, I hope I didn't hear what I thought I heard. So what is the COC in organic chemistry? How about if I draw one? What does it look like if I draw this? Yes, thankfully I have written class. What? It's an ether, right? And so the idea is hemi means it's half alcohol, half ether. So hemiacetal means half alcohol, half ether. At the end of a molecule has a hydrogen there, meaning the hemi part's the halfsies. The acetal says it's at the end and has a hydrogen, right? Kind of makes sense?
What's the difference between, oh, you're just saying heavy means half OH?
Right, meaning it's got one OH group and one OR group, right? Because what we can have next is an acetal and a ketol. So the idea is that we're going to go from aldehyde to hemiacetal to acetal, and we're going to go from ketone to hemiketone ketol to a full ketol. And so an acetal, because it comes from an aldehyde, has this, right? This is the acetal, or the fact that it's from an aldehyde. And it has two ether groups, so it's not a hemi, it just has both our ethers. And then the way that that differs from a ketol is simply that instead of an H, there's an R because it's the ket part. I mean, I guess instead of acetal, you could call it alditol, which actually makes more sense. Kind of sounds good too. But I'm not allowed to go back and just randomly rename things to be better. Otherwise, it'd be awesome if Jen were in charge of chemistry. Like, we just hired me to be president of chemistry and I could just do anything I want. Like our current president. So, the series of reactions we're going to talk about next are, I call them acetal-ketol reactions. That's as good a name as any. And so there's two steps. And we're going to kind of talk about them in, at the same time. The first step is we're going to have aldehyde plus alcohol goes to hemiacetal. And then obviously a ketone plus an alcohol goes to what? Yeah. So remember, one of the nice things about, I guess I'll spell it all the way out. And one of the nice things about aldehydes and ketones is you almost get 2-for-1 deals. Meaning, anytime an aldehyde reacts, ketone just about does the same thing. The only time a ketone and an aldehyde react differently is when? Oxidation, right? And that's even better because then you only have the aldehyde reacting and the ketone is just a no reaction. So start getting these ideas in your head. Start going, okay, I know that it's an aldehyde and a ketone are going to react the same way. So I really only have half as many reactions as I think I have, right? And then I'll put it down. We'll see if we get to it. Step 2 is I can take that hemiacetal and I can add more alcohol to it. And I can make an acetal plus H2O. And then, of course, if I take my hemiketol plus an alcohol, I can make my ketol plus H2O. And what we're going to see is that that first set of reactions is simply addition. The second set of reactions is dehydration. And the reason the first set is addition is we have a carbon double bonded to an oxygen. So when you see carbon double bonded to an oxygen running around, you should be thinking one of two things usually. I'm either going to oxidize that puppy or I'm going to add that puppy. And then you should think, oh, puppies are cute. And then for the hemiacetals and hemiketols, you should realize the only thing I've got is an OH group. And so one of the logical things when I see an OH group is to always think that a dehydration could occur. Okay, so let's take a look at that first reaction. So I've got my aldehyde. Now, be careful. Ask for how many actual seconds you want, because 2 seconds isn't much. Okay. So, oops, I guess we put it on the top. Now, I said that this is an addition, right? So when you think about addition, what physical process are you thinking about? So what gets added to the oxygen side of the double bond? And what gets added to the other side? That oxygen. So this reaction and a cyanohydrogen reaction, if you ask me personally, it's the same reaction. As long as you think addition and know how to break it apart, it's the same process. So I get something that looks like this. I get my OH, and then I get a bond to oxygen, and then I copy down the rest of the molecule. So, I've got 1, 2, 3, oops. Oh, wonderful, we crashed it. Oh well, it's about time we crashed something. We've been having too much good luck. As much as I love computers, at the current time in life, I'm kind of tempted to say, fuck them. Oops, I said that on tape. I didn't mean you, computer. I like you. You're a good computer. We'll finish with this reaction. It's easy though. So we had our, oops. We had our aldehyde. We had our alcohol. We made our OH. We had our H going over here. We had our O going there. And notice if you just connect the parts together, meaning if I break that double bond, I know that I had something there and I add something there. And if I break this, I know I add there and I add there, right? Meaning it literally is connecting the pieces together. And so we make our hemiacetal. And here's my alcohol part. That's those 4 carbons here. If I do the corresponding thing with a ketone, we'll just add a short alcohol. Same exact process is happening. That hydrogen is being added up here. That oxygen is being added to the other side. So I take my molecule the way it started. I end up with an OH on one side and an oxygen to 2 carbons on the other side. And so this is a hemiacetal and a hemiketal. You can tell that it's the that's the acetal whether there's a hydrogen there, right? And you can tell it's a hemi because it's an alcohol and an ether on both of them. So these are the hemis. Well, let's go ahead and stop here. What we will do is we'll pick this up on, gosh, I'm half tempted to say we'll do some of it on Thursday and we'll actually do lab on Friday maybe. We'll see. That way you guys get more chance to ask questions. You can work on it Thursday night and ask questions Friday. Do you guys what do you have on Friday? Does Todd have class? Yeah, so we'd have a short day. We'll see. Probably just do lab. What I would start doing is start working on that reactions homework because that is,